A new space race is igniting, fiercer and more far-reaching than the one that once captivated the world in the heat of the Cold War. Back then, the United States and the Soviet Union raced to plant a flag on the moon, one small step for man that quickly turned into a giant leap for geopolitical bragging rights. But that chapter, historic as it was, is now just a prologue. What's happening today isn't about reaching the moon, it's about building there, staying there, and transforming its barren surface into the next great frontier for humankind. And leading this new era is a name that barely existed during Apollo's golden age, **SpaceX**, under the relentless vision of Elon Musk. While the US, China, and Russia angle for dominance in low Earth orbit, Musk has his eyes locked on something far more enduring, Moonbase Alpha, the first permanent human outpost on another world. This isn't science fiction anymore. It's engineering. It's logistics. It's raw determination married with cutting-edge innovation. It's also high-stakes geopolitics, with superpowers silently acknowledging that the moon isn't just a rock in the sky, it's strategic real estate, a stepping stone to Mars, and possibly, the future headquarters of off-Earth civilization. And Musk, never one to wait for permission or play by traditional rules, has already set the course. After months of political distractions and media storms, Elon Musk has returned to the very heart of SpaceX, Starbase ***, a growing metallic city on the edge of the Texas Gulf Coast, where launch towers claw at the sky and the sound of raptors roaring fills the humid air like thunder. It's here that Musk has regrouped, refocused, and reignited his lunar ambitions. With the prototype-heavy Starship assembly lines buzzing, launch pads being rebuilt, and orbital missions inching closer to regularity, the message is clear: this is no longer an experiment, it's a countdown to permanent presence beyond Earth. And the moon is the first destination. During a recent keynote, Musk laid it out with his usual off-the-cuff genius, raw but loaded with clarity. "We should have a moon base," he said simply. And not just any base. A structure built not for a photo op, but for life. A proving ground for the technologies that will one day carry us across the void to Mars. Because, as Musk often points out, the moon sits a mere 225,000 miles away, a distance that's practically next door when compared to the staggering 34 million miles to Mars. A Mars mission takes half a year, one way. The moon? Days. The moon gives us a lab, a training ground, and a launch pad. And we've got to prove we can build, live, and sustain off-Earth before we take on the red planet. So, how does Musk actually plan to do it? It starts with Starship, and more specifically, a highly customized version of it, the Human Landing System, HLS, variant. Unlike the cargo or point-to-point Earth versions of Starship, this lunar-focused model is built solely for operations on the moon. In a move that stunned traditional aerospace contractors, NASA awarded SpaceX nearly $2.9 billion to build this lunar lander for the Artemis 3 mission, the first time since Apollo that American astronauts will walk on the moon again. And walk they will, not on the equatorial regions like Apollo, but near the moon's south pole, where permanently shadowed craters may hold the holy grail of long-term habitation, water ice. Artemis 3 is not just about planting flags. Astronauts will deploy robotic scouts, gather mineral samples, conduct solar radiation tests, and begin mapping potential locations for future structures. And with the HLS Starship as their lander, they'll be stepping onto the most advanced spacecraft ever designed to touch lunar regolith. And the hardware? It's already being built. Though SpaceX has remained predictably quiet about internal progress, eagle-eyed observers spotted key HLS components earlier this year inside the Star Factory, SpaceX's high-tech, assembly line-style rocket workshop. Massive, pale white hardware was seen under construction, possibly parts of the HLS body and access hatches. Meanwhile, NASA shared its own test footage of a full-scale elevator prototype developed with SpaceX, an essential feature of the moon lander. Unlike the Apollo lunar module, which was only a few steps from the surface, the Starship HLS towers several stories above the ground. An astronaut cannot simply climb down. A reliable mechanical elevator will ferry crew and cargo from the airlock down to the moon's surface and back up again, time after time. In the test, engineers evaluated door latches, ramp systems, and even simulated how the basket feels when it moves vertically with gear and astronauts on board. The results? Promising. But all of that pales in comparison to the greatest challenge, fueling in space. To reach the moon with a fully loaded lander, Starship must be topped off in low Earth orbit. That means orbital refueling, a technology never before attempted at scale. The concept is as bold as it is crucial. Multiple Starships will launch, one carrying the lander and others acting as tankers. Once docked nose-to-nose in orbit, one tanker will transfer vast quantities of liquid methane and liquid oxygen to the lander. Only when topped off will it begin its journey to the moon. It's not just futuristic, it's revolutionary. And it's a linchpin in Musk's entire lunar strategy. Without orbital refueling, no lunar cargo, no lunar lander, and definitely no base. Musk has publicly promised a full-scale demonstration of this process as early as next year, one of the most anticipated moments in spaceflight history. So with all these pieces, HLS, refueling tech, robotic scouting, what exactly is Moonbase Alpha? Picture a base roughly 500 square meters in size, the equivalent of 2 decent-sized suburban homes. That doesn't sound like much, until you consider that everything has to be flown to the moon, landed, offloaded, and then assembled in an environment with no air, no water, and wild temperature swings. Even with a minimalist design, building such a base requires about 1,000 tons of materials. That's where Starship's raw power comes into play. With its 42 Raptor 3 engines, 33 on the booster, 9 on the lander, it can haul up to 200 tons to the moon in a single flight. That's double the payload of the legendary Saturn V. So, to deliver enough material for a basic Moonbase Alpha, SpaceX will likely need about 5 Starship flights. Now imagine this, one of those HLS landers touches down on a flat, well-scouted lunar site. The massive cargo bay opens, and out rolls a fleet of autonomous robots and rovers. The first task: offload every ounce of construction material to lighten the ship. Then, something bold, the ship itself is lowered onto its side, transformed from a vertical rocket to a horizontal habitat module. Think of it like turning a skyscraper into a ranch-style home. Non-essential components, auxiliary engines, external tanks, are removed to shift the center of gravity and improve balance. Meanwhile, internal systems stay pressurized to maintain structural strength. Leftover propellants are carefully pumped out into dedicated storage tanks, possibly to power other systems or stored for future launches. And now you have it, the empty propellant tanks and cargo bay are repurposed. They become living quarters, laboratories, cargo storage, and environmental systems housing. With nearly 800 cubic meters of usable interior volume, that single Starship turn habitat offers more than twice the habitable space of the entire International Space Station, which only has 388 cubic meters. Imagine that, a single spacecraft doubling humanity's current orbital living space, but this time, on the moon. Once this internal conversion is complete, insulation panels and radiation shielding are installed to protect from solar storms, cosmic rays, and extreme thermal fluctuations. Walls are outfitted with equipment racks, bunks, food preparation stations, air filtration systems, and water reclamation tanks. The interior is then divided into zones: sleeping quarters, command modules, med bays, hydroponic stations, and emergency safe rooms in case of decompression or flare events. There's even talk of 3D printing some furniture and bulkheads using lunar regolith mixed with polymers flown in from Earth. Every inch of space counts. Every item has to earn its keep. To support the needs of astronauts and sustain ongoing scientific missions, the next critical phase involves connecting the infrastructure, laying down the complex web of cables and pipelines that will deliver communication, power, oxygen, water, and data across the base. These systems, often buried or shielded with regolith to avoid radiation interference, form the veins and arteries of Moonbase Alpha. Everything depends on their flawless operation. And once those systems are in place, human presence becomes more than just a test, it becomes the beginning of a long-term future. The first explorers will survey the unforgiving terrain of the lunar South Pole, inching their way across jagged shadows and lightless craters where temperatures drop to hundreds of degrees below freezing, and where hidden beneath the dark soil, frozen water may lie trapped like a precious ancient resource untouched for billions of years. To find it, they won't be alone. Robotic scouts will lead the way. Machines like NASA's Viper rover, designed to sniff out hydrogen and trace volatile compounds, will crawl across the surface, drilling, scanning, and mapping the most promising deposits. These robots are more than tools, they're trailblazers, marking where humanity can safely dig, build, and perhaps one day drink. But this isn't about building cabins on the surface or landing fancy habitats with windows and solar panels. That vision, as beautiful as it may seem, leaves us exposed. Micrometeoroids still race through space like bullets, the lunar surface is constantly battered by solar radiation, and the thin layer of regolith offers little protection from deadly cosmic rays. That's why the next phase of construction moves underground. Natural lava tubes, massive cave systems created by ancient volcanic flows, could offer safe, ready-made shelters. Their arched ceilings and thick walls provide a natural shield from radiation and impacts. Where these don't exist, engineers plan to carve artificial tunnels using robotic boring machines, building out research zones, sleeping quarters, and life support compartments beneath the surface. These dugout areas will become the backbone of lunar living, stable in temperature and shielded from all external threats. The shelters will be reinforced not with materials flown from Earth, but with the moon's own soil. Lunar regolith, once viewed as just dust, is quickly becoming our most valuable building material. It's rich in silicates and oxides and can be transformed into geopolymer concrete using on-site processing systems. By mixing regolith with binding agents, and in a strange twist of science, even incorporating urea from astronaut urine to enhance flexibility, teams can 3D print structural walls, arches, and barriers directly on the lunar surface. What once seemed like science fiction is becoming a practical necessity. And the more we build from what's already there, the less we depend on Earth. That's the key to sustainability. The more we reduce launch weight, the more permanent our presence can be. Despite how iconic the image is, a few astronauts walking in suits under the harsh lunar sky won't be enough to get the job done. As inspiring as that might be, astronauts have limited range and mobility. Space suits are bulky, movement is slow, lifting power is minimal, and exposure to the abrasive lunar dust, sharp as glass and electrostatically clingy, can wear down joints, seals, and suit linings within days. And then there's the radiation. With no atmosphere above, every minute spent outside increases the risk of radiation damage to human tissue. Even a solar flare could force immediate sheltering. That's why robots, again, become the workhorses of lunar construction. Machines that don't sleep, don't breathe, and don't need to be protected from radiation are essential. These autonomous systems will dig trenches, lay cables, haul supplies, print structures, and process resources 24 hours a day. One of the most promising machines in development is NASA's ISRU Pilot Excavator, IPX. It's not just a digger. It's a technological gateway to lunar independence. By heating regolith in a controlled environment, IPX can extract pure oxygen directly from the soil. Since regolith contains compounds like silicon dioxide, iron oxide, and aluminum oxide, which all trap oxygen in their molecular structure, the machine can use extreme heat to break these bonds and release the oxygen into storage tanks. That oxygen can then be used for breathing or for fuel production. Current methods can extract roughly 0.2 kilograms of oxygen from every kilogram of regolith, which is enough to keep a single person alive for 6 hours. Scaling this up, 100 kilograms of regolith per day could sustain a 10-person crew without ever needing Earth resupply. That's a milestone in deep space living. And it's just the beginning. More advanced reactors could dramatically improve these yields, giving Moonbase Alpha the tools to fuel Starship for return trips or even power other outposts in the future. Water is no less essential. SpaceX recently launched NASA's Lunar Trailblazer mission aboard a Falcon 9 rocket, a small spacecraft equipped with infrared spectrometers to map the distribution of water on the lunar surface. While it suffered a technical glitch shortly after deployment, the mission revealed something critical: the presence of water is real, and likely widespread in shadowed polar craters. With that data, robotic diggers will be sent to those locations, boring through the frozen regolith to retrieve ice crystals locked beneath the surface. Once collected, the ice will be melted, filtered, and stored in pressurized tanks for use in everything from hydration to hygiene, to growing crops. Even wastewater can be reclaimed, passed through filters and purifiers until it's clean enough to re-enter the cycle. On the moon, every drop is precious. There's no such thing as waste. But surviving long-term isn't just about air and water. It's also about nourishment. The freeze-dried rations used aboard the ISS may work for short missions, but over time, their nutrient content degrades. Critical vitamins, especially C and B1, drop to levels too low to keep astronauts healthy. Plus, high salt and sugar content make them unsuitable for long-term wellness. That's why growing fresh food on the moon isn't just a luxury, it's a requirement. Scientists have already managed to grow plants like Arabidopsis thaliana, a mustard green relative, in lunar regolith collected during the Apollo missions. This hardy plant, well-studied and adaptable, thrived in simulated conditions. The next step is to grow it on the moon itself, in tightly sealed, thermally controlled greenhouses. These greenhouses will feature artificial lighting systems, automated oxygen and CO2 regulators, hydroponic trays, and water recycling systems. If successful, they'll support an ongoing food supply, allowing astronauts to eat leafy greens grown just meters from where they sleep. But growing food brings us back to a crucial issue: oxygen. Plants need it to thrive, but so do people. A single astronaut uses far more oxygen than a greenhouse of plants can produce. That's why tapping into the lunar regolith to mine oxygen remains an absolute priority. The moon is rich with the element, it just takes the right tools to free it. Using high-powered lasers to simulate sunlight, scientists can melt regolith inside specialized carbothermal reactors. The extreme heat breaks down the molecular structure of the soil, releasing oxygen in gas form. This oxygen is then pumped into storage tanks, pressurized, and distributed throughout the habitat. With consistent operation, this method can sustain entire crews for extended periods. And as these systems grow more efficient, lunar greenhouses won't just be viable, they'll be scalable. Once all the survival systems are in place, the next challenge is connectivity. There's no mission without communication. And for that, SpaceX is looking beyond just antennas and satellites. The Starlink network, originally built to bring high-speed internet to remote Earth regions, is evolving. Starlink 53, a new class of massive orbital platforms, is in development, each roughly the size of a Boeing 737 and capable of beaming high-bandwidth connections from lunar orbit. Once deployed, these satellites will create a digital web around the moon, allowing live video feeds, telemetry, voice communication, and even real-time control of autonomous systems. Mission control on Earth could guide a rover across the moon's surface with almost no delay. Astronauts could video call their families from inside the base. Scientists could live stream experiments from hundreds of thousands of miles away. The era of lunar silence is over. We're entering the age of the connected moon. And when you step back and look at it all, every piece fits like clockwork. SpaceX handles the launch and landings. The Boring Company develops tunnel digging and habitat carving systems. Tesla brings in robotic autonomy and machine learning to operate and maintain systems with minimal human input. Starlink forms the bridge between worlds, providing uninterrupted communication. And with Neuralink, someday even astronaut stress levels or cognitive fatigue could be monitored and treated in real time. What seems like 5 separate companies is, in reality, one tightly woven machine. Each part supporting the other, all driving toward a single goal. The goal is not just to land. Not just to visit. It's to stay. To build. To live. Moonbase Alpha is more than a structure. It's the blueprint for how we expand as a species. It's how we learn to take root beyond Earth. And every trench dug, every tank filled, every line of code written for lunar machines brings that vision closer. What once took an entire nation's space program now happens at the hands of a private company, accelerating not just progress but expectation. Because now, people